Hey everybody, it's Miss Berry. This is going to be the part 2 of our section 1.2 lecture video. So I'm going to go ahead and flip the camera over and we'll get started. Alright, so where we left off, we were right here at scientific notation. So I'm going to read the definition to you of scientific notation. I'll talk about the little word of caution at the end and then we'll do some examples. So a number is in scientific notation when it's written in the form a times 10 to the 10th, where the absolute value of a is between 1 and 10, and n is an integer. So absolute value of a, so that means that this number here, the absolute value of this number right here must be a number between 1 and 10. So just to remind you of what absolute value looks like. So if you had the absolute value of something like -4, it would be +4. So its absolute value is the distance that number is from 0. Distance is always positive. If you had the absolute value of something like +5, it would just be 5. If you had the absolute value of something like -2.4, it would just be +2.4. Okay, so you get the picture. And it says the n is an integer, so that means that n is going to be a number like -1, -2, -3, or it could be +1, +2, +3. It could also be 0. It says if n is a positive integer, then the number is large in magnitude. So if the exponent is positive, then the number is going to be really big. And if the exponent is negative, that indicates that your number is very close to 0. It's small in magnitude. And it says the number a itself can either be positive or negative. So this number a can be positive or negative. It's just as long as its absolute value is between 1 and 10. And the sign of a, so whether a is positive or negative, that determines the sign of the number as a whole. And then the word of caution here says the sign of the exponent in scientific notation does not determine the sign of the number as a whole. Remember, we just said that's what the sign on a determines, not the sign of the exponent. The sign of the exponent only determines if the number is large. So if your exponent is positive, that's a really large number. And if your exponent is negative, it's a small number, it's close to 0. Over here, I just included this little note from the textbook of how you can display or express scientific notation on your calculator. So if you have a Texas Instruments calculator, if you hit the second button and then the comma, that pulls up the little E button, and that's how you express scientific notation on the calculator. Every once in a while, you'll get a problem when you work it out on the calculator, it will express the answer in terms of E like this. And so if you see that, just know that that's scientific notation. All right, so let's look at a couple of examples. It says convert the number from standard notation to scientific notation. All right, so we know that scientific notation looks like this, a times 10 to the n. And a has to be a number whose absolute value is between 1 and 10. So right now, this number is much too small to be between 1 and 10. So we got to move the decimal over so that we can figure out how many places that we need to move the decimal over to make this number something that's in between, whose absolute value is something in between 1 and 10. So 1, 2, 3, 4. If we move the decimal right there, that would be negative 4.47. And the absolute value of negative 4.47 is just 4.47. That number is definitely between 1 and 10. All right, so we move the decimal over 4 times. Now think about this. This is a number that's really close to 0. It's really small in magnitude, so that tells us that our exponent should be negative. Remember, the sign on the exponent determines whether the number is really large or if the number is really big. And it tells you how many times to move the decimal over. All right, so let's see how many times we moved the decimal. We moved it 1, 2, 3, 4 places. So it's going to be negative 4. Write that again. It kind of looked like a 9. There we go. All right, so let's look at our next example. convert the number from scientific notation to standard notation. All right, so we have a times 10 to the n. All right, here's our value for a. It's definitely a number, but that's whose absolute value is between 1 and 10. And then here's our exponent is 5. It's positive, so that means it's going to be a really large number. So this is going to be a really large number. All right, so we're going to write 7.58. And now we're going to move the decimal this many places. We're going to move it 5 places. We're actually going to move it to the right this time because we know it's supposed to be a really large number. So if we moved it to the left, that would put zeros over here. It would become a really small number. So we want to move it to the right 5 times. 1, 2, 3, 4, 5. Fill in those blank spots with zeros. So there you go. Our answer is 758,000. Okay, so that's scientific notation. Just a couple of examples. There's only a couple of problems on the homework about this. Right now, we're going to move on to our last topic, which is about radical notation. This is an example of radical notation. Here we would read this out loud as the nth root of a. All right, so this little symbol here that looks kind of like a check mark, that's the actual radical. So that is the radical. This number here is called the index. And there's one thing I wanted to point out about the index before we move on. I'm going to type it out just so it looks a little bit neater. If there is no number indicated in the index, then we assume the index is 2. And this one has a special name. This radical has a special name. This is called a square root. Let's make that purple so it kind of matches with the index. Right there. There we go. If there's no number indicated in the index, then we assume the index is 2. This is called a square root. And then the number that is inside of the radical, or the expression that is inside of the radical, is called the radicand. All right, so the number or the expression that is inside of the radical is called the radicand. All right, so let's read over the definition for radical notation, and then we'll do some examples. A lot of the questions that are on your homework can be done with your calculator, so I'll show you how to do that. It says the definition of a radical notation has 2 cases. The first case is where your index, again, remember the n represents your index. Let's just write that there. N is the index. All right, so if the index is an even natural number, so that's going to be something like 2, 4, 6, and so on. So if your index is an even number, so it says if your radicand is a non-negative real number and the index is an even natural number, then the nth root of a is going to be equal to the non-negative real number b that has the property that b to the n equals a. All right, so I'm going to show you what that means. Right, so if we say we have something like the square root of 16, we know that even though it's not indicated here, we know that we can assume that the index is 2. Okay. So what this definition right here says is that this is equal to the some number b, where if you square b, let me write this in a different line. This is equal to some number b that when you square it, you get the radicand. So some number where if you square it, you'll get 16. So think about it in your head. What's the number that if you squared it, if you multiplied by itself, that it would give you 16? That would be 4, right? So b is 4. And this is what we would call a perfect square. because whenever you take the square root of this number, it comes out to a integer value. So that's a perfect square. And then it has this property at the very end. It says, note that the nth root of a raised to the n is equal to a, and the nth root of a to the n where the the exponent is inside the radical, so it's in the radicand. Same thing, it's also equal to a. So let me just show you what that means. So if you had something like this, let's say you had the fourth root of 2 to the 4. If your index matches your exponent, they're going to cancel each other out. Okay, so the square root, or excuse me, the fourth root here would cancel out the fourth power, and this would just be equal to 2. All right, the second case is where your index is an odd number, so like the third root, the fifth root, the seventh root, something like that. It says if a is any real number, so if the radicand is any real number, it can be negative, it can be positive. Remember, for the first case, when the index was even, it had to be a non-negative number, so that means positive or 0. But for the case where the index is odd, the radicand can be negative, or it can be positive. Or it can be 0. It says, so if the radicand is any real number and the index is an odd natural number, then same definition. The nth root of a is the real number b, whose sign will be the same as the sign of a, with the property that if you take b, you raise it to the index, it's equal to the radicand. So let me show you an example of that. Let's say we had the cube root of 27. So what this definition says is that the cube root of 27 is going to be some number b that when you raise it to the third power gives you back the radicand, which is 27. So you may not be able to think of this one off the top of your head, but what's some number that when you multiplied it by itself 3 times would give you 27? That would be 3 times 3 times 3. So 3 times 3 is 9, 9 times 3 is 27. So b would be 3. And that's an example of a perfect cube. This paragraph down here, this is what I talked about up here at the top, so we'll skip that. All right, and then we talked about perfect squares and perfect cubes, so let's jump to our examples. All right, so I'm going to show you how to plug these in your calculator. Whoops, wrong thing. There's my calculator right there. I'm going to make it so that most of the screen is our whiteboard. All right. So get your calculator, clear out your screen. The first example we have is the fifth root. So the fifth root of negative 32. So you could go and use the definition like how I showed you with those perfect cubes and the perfect square earlier. But this is going to be the easier way to do it. So let me show you a little bit. I'm going to open up the calculator and make it full screen for a second. If you look right here, can y'all see at the very bottom? There's the square root. So if you're doing a square root, you would just hit second x squared. That pulls up the square root. Otherwise, you're going to have to go to that math button. Right, see there, that's the cube root, the third root. And then for any other roots, you're going to go to option number 5 here. Okay, so let's look at our first example was the fifth root of negative 32. All right, so that one is one of our, whoops, hit the wrong button, my bad. So that's where we're going to have to use this option number 5 here, but it's important that you type in the index first. Okay, so the index is 5. It's the fifth root. So type in 5 and then go to math and go down to option number 5. And I have a TI-84 Plus CE, so this is one of the newer calculators, so you can see how it puts the little 5 in the index. Yours may kind of like leave it more out front, which is fine, depending on what version of the calculator you have. Right now on the inside, we're going to type negative 32. Make sure that you're using this negative button down here at the bottom and not the minus. Okay, so we're going to type in negative 32. Hit enter, and there's our answer. Oh, look, my calculator's about to die. Maybe it'll live through this video, but with my luck today, it probably won't. All right, so we're going to type in write in our answer. Our answer was -2. All right, so now we have the fourth root of -16. And basically what this means is that if you took, remember what we said before, if you took -2 and you raised it to the fifth power, that would give you back -32. So that's what the definition of a radical means. All right, so fourth root, so type in 4 because that's the index. Fourth root, to go down to option number 5 of -16. Non-real answer. So that'll be one of your options. We'll just say non-real answer. And the reason that we got a non-real answer here, if you remember when we talked about the definition before, it said that if you have an even index, the number is supposed to be either 0 or positive. Otherwise, you get a non-real answer. Right, number 8 is the cube root. All right, clear that out. The cube root of 27/64. So go to math. Remember, we have a special little button for the cube root. So 27 divided by 64. I literally just used this divided by button right here. 27 divided by 64 is 0.75. Now, they probably want the answer in the form of a fraction. So let me show you how to convert that to a fraction. You just hit the math button. And then you see that little arrow, that means convert to a fraction. Hit enter. So this says convert the answer to a fraction, 3/4. Okay, 3/4. All right, and then I wanted to show you this example here. I just copied this straight out of the homework. I was getting a little lazy. I didn't want to write it all out. It says, determine if the following radical expression is a real number. If it is, you should evaluate the expression. And then it says, select an option to display the text boxes needed to complete your answer. So we'll just circle whichever one it is. Okay, so let's type this in our calculator. It's a cube root, so we're going to go to math, down to the cube root of -27. Now, this should be a real number because remember, with odd indexes like 3, we're allowed to take the cube root, in this case, of a negative number. It's just with even indexes that you can't. All right, so hit enter. Obviously, there was no error message, so this was a real number. All right, so we'll say this was a real number, and the answer is -3. Oh, that looked awful. Let me try that again. There, that's better. Okay. I'll try to finish these before my calculator dies. All right. And before I have to go to class, I have class at 12:30, so maybe let's see. Can we finish this in time? Yeah. All right, so this last part, still about radical notation. The topic is specifically simplifying and combining radical expressions. It says a radical expression is in simplified form when the following conditions are met. The radicand, remember that's the number or expression inside of the radical, contains no factor with an exponent that's greater than or equal to the index. The radicand should contain no fractions. And the denominator, if there is one, contains no radical. And the greatest common factor of the index and any exponent occurring in the radicand is 1. So that means the index and the exponent in the radicand should have no common factors other than 1. And these are the properties of radicals. Right, so the first one says, if you have the nth root of a times b, you can separate that into 2 radicals. Let me make this full screen. You can separate that into 2 radicals. The nth root of a times the nth root of b. You can also separate this across division. So you have the nth root of a over b is equal to the nth root of a divided by the nth root of b. And then the last one says if you have the nth root of the nth root of a, then you can combine those radicals. You just multiply their indices. So that would be m times n, the m times nth root of a. And then they have some examples here. And you can pause the video if you want to go through those examples. Like I said, I have class in like 14 minutes, so I'm trying to get through these a little quickly. I'm going to show you how you can rationalize the denominator. Remember, it said that your expression is going to be in simplest form if you don't have any radicals in the denominator. All right, so this is a simple problem. If we have any more complicated ones, I'll make a separate video. But if you were going to rationalize the denominator here, that means rationalize the denominator means eliminate all radicals from, sorry, I was pressing a button on my pen, from the denominator. Okay, so we're eliminating all of the radicals from the denominator. And what's kind of cool about these is that you can just multiply them by themselves, and that will get rid of it. Really cool property of radicals when you have just one term down here. All right, so this -8 is just going to hang out in front. We'll have -8 on the square root of 3 times y divided by. Now, another way we could write this, the square root of 3y times the square root of 3y, that would be like the square root of, here we don't even need a parentheses, we'll say the square root of 3y squared. Now y'all remember, this is a square root, this is a squared, so those are going to cancel each other out. So bang, bang, those cancel out. And look at that, already we've gotten rid of our radical down there. -8 times the square root of 3y over 3y. And then you just make sure that there's nothing you could simplify. -8 and 3 do not have any common factors. 8 and y, or -8 and y, do not have any common factors. These can't cancel because one's inside of a radical. So you're done. This is our simplified answer. So that's how you rationalize the denominator. You just multiply. If you have a simple radical in your denominator like this, you would just multiply it by itself in the top and in the bottom. All right, so this one says combine the radical expressions if possible. All right, so let's think about each of these. All right, so we have the square root of 8 times y cubed plus 8y times the square root of 2y. I'm going to start by just ignoring this one for a second. I just want to talk about this piece. Remember we talked about just a minute ago, we said that radicals in simplest form if nothing has an exponent greater than the index. None of the terms should have an exponent greater than the index. Here the index is 2. So the exponent on both of these is 1. Okay, so that's good. That tells us that part's in simplest form. The number here is 2. 2 has no factors other than 1 in itself, so we can't break that down any further. So we know that this part is in simplest form. Now let's look at this part. I'm going to actually take it off by itself over here, just to try to make it look a little bit more simple. Let's think about the number 8. You want to think of ways or numbers that would multiply to give you 8. And one of which was a perfect square. All right, so think about numbers that would multiply to 8. That would be like 4 and 2, right? So 4 times 2 is 8, and 4 is a perfect square. And then similarly, we could kind of do something for y here. We could break that up and write it as y squared times y, because we know the square root of y squared would just be y. Okay, so now I'm going to separate this into several pieces. We have the square root of 4 times the square root of 2 times the square root of y squared times the square root of y. So notice I just put each little piece inside of its own radical. All right, so the square root of 4, we know that's 2. Square root of 2, that can't break down any further. Right here we have a square root, and this is being squared, so remember what that does. They cancel each other out. That just leaves you with y. And then we have square root of y. Right, so I should have been putting little equal signs every time. Combining this all together, we have 2 and y that's going to go out front. And then inside the radical, we have 2 and y. Okay, so that's this first piece. We have 2y on the square root of 2y plus 8y on the square root of 2y. Now, in order for you to add or subtract radicals, they have to have the same exact expression in the radicand. And these do, so they both have a 2y in the radicand. So you're just going to add their sort of coefficients, if you will, like the number that's on the outside of the radical. So 2y plus 8y would be 10y. So all I did was I took and I did 2y plus 8y gives you 10y. And then my radicand, or my radical, excuse me, it's got to stay the same. So that's square root of 2y, and we're done. So you're just combining those pieces, just like if you had something like 2x plus 8x, that would be 10x. You have 10y out front, so that's kind of like the 10 part. And then this is the like terms part, the square root of 2y, so that just gets stuck on the end. Okay, we have a couple more. All right, so this one we're going to do in our calculator, so let's get that pulled up. Anytime you're dealing with a problem and it's just numbers, you can probably do it in your calculator. So let's clear this out. We have parentheses, so have a little open parentheses right above the 8. We have negative 27. Make sure you use the negative button, not the minus, over 1,000. Close parentheses. Raised to the negative 2 divided by 3. Okay. And there you go. Well, we should probably write it as a fraction, right? So go to math, frac, and there we go, 100 over 9.